Upon identifying a research question, the next step is to identify a good working research hypothesis, or you may actually develop a few hypotheses. Now, remember, the research hypothesis is more specific than the research question. So this research hypothesis is something that ideally will be testable. Now, as we go forward, there's a big caveat in research methods that I want to cover regarding this presentation. Not all scientific research is hypothesis driven. There's a good bit of research that's done out there that is descriptive research, or sometimes called discovery science. And in some cases, some people may not use the most flattering language for descriptive research or discovery science, but yet it does play an important role. So some examples of descriptive research may include what is sometimes called data dredging, or more pleasantly described as data mining, where researchers may go through large volumes of data and just look to see if there are any statistically significant correlations or any patterns that may exist. And they may do so without any preconceived hypotheses or preconceived notions for why those correlations or patterns would exist. They could potentially develop future hypotheses from this, but you would call this kind of discovery research. They find patterns and then they may develop hypotheses that can then be used to test whether or not their explanations for why those patterns may exist. But the type of research we're talking about mainly in this class is a priori hypothesis driven research, meaning that your hypothesis is developed before you actually get into the data. There are other types of non-hypothesis driven research that would fall into the descriptive research category, and this would include medical doctors describing new cases of disease. They are just documenting what they observe. They're just looking at everything. Biologists identifying new species of maybe bacteria or new species of viruses or new animals. Inventors who are tinkering with things, or engineers designing things, may engage in descriptive research where they're not really for sure why what they're going to do will make something better or worse. They just tinker with it and then see what happens, and they may not necessarily actually have a hypothesis going into it. And then upon actually making it better or seeing it make an improvement, they may then come up with a new hypothesis that they can then test and maybe make their invention better. So just keep that in mind. Now, if you're trying to get grants for a company or a government or a research enterprise or a university, it is important to know that agencies of the government, like the National Institutes of Health, they typically do not fund research lacking hypotheses. And the Centers for Disease Control and Prevention, sometimes that's the same, but sometimes CDC does provide research money that is for surveillance only. Are the mosquitoes there or are they not? So that's important to know. The National Science Foundation also sometimes funds descriptive research, but by and large, the majority of research funded in the United States is, in fact, hypothesis-driven. So let's get into hypothesis-driven public health research. When you develop a hypothesis in public health, the assumption is the hypothesis you're coming up with is original and testable. Also, it is understood that the hypothesis is going to be specific and not overly general. It's going to be specific to wherever you think you're going to be getting your data from. The hypothesis should not be overly complex. It should not have a bunch of ands and ors. It should be simple. You're going to test one thing with that hypothesis. And there's also an assumption that the hypothesis that was developed is based upon prior observations by either the person doing the study or prior observations from others where their observations have been documented in the peer-reviewed literature, and that there's some sort of justification for why the hypothesis that's being presented was actually developed. There should be a justification. It shouldn't just be a guess. There should actually be scientific reasoning based upon literature or prior observations. So the well-designed hypothesis should actually be able to be testable. Now, in environmental health in particular, often the hypothesis will be testable using quantitative methods. In quantitative designs, statistics are commonly employed. Now, statistics are not able to just work miraculously at the very end of a data collection effort to create something for the investigator. It don't work that way. In quantitative designs, statistics should be consulted and considered in advance of the data collection so that you can be assured that the data you are collecting are going to be collected in a manner whereby the statistics that will then be employed after the data are collected will be able to actually evaluate whether or not the hypothesis was correct or whether or not the hypothesis was unable to see an association or an effect. So it's important to think about that going into your data collection. Now, the hypothesis also should be original in nature, meaning that if the work has already been proven, then that's background research, and that would not qualify as an original hypothesis. In this case, the research that's going to be done is going to be research that will make your research be considered foreground research or novel research. So how might your data be collected to address novel research questions and a novel research hypothesis? Well, you can study a unique population of people, or it could be based on race, ethnicity, geography, income status, occupation. There's a variety of ways that you can make your research novel. Potentially novel exposures. There's insufficient evidence that's out there on one particular chemical or a particular type of exposure that people may have. I mean, you might be looking at bicyclists. You may look at workers in certain scenarios. Another element that may make your research novel could be other studies that have been done, but they had certain limitations. They maybe didn't ask a certain question in their questionnaire and couldn't adjust for some particular confounding variable because they didn't ask about it. And now you're going to ask about it to see whether or not that confounding variable actually makes a difference. You may also use a different study design related to the same research topic. They may have used an ecologic design, and you may be using a cross-sectional survey. So there are a variety of ways, and there are other ways that are out there whereby you could develop an original hypothesis. When hypotheses are developed, they should not be overly complex. Ideally, the hypothesis should be able to be narrowed to a specific population that would allow the results to be generalizable to that particular group and potentially to some other groups, but definitely within that group. You should avoid using "and" statements. So we think that there will be an association between X and Y and X and Z. No, we don't want that. That's too many. If you're going to have "and" statements and you're going to be evaluating two things at the same time, then write out two hypotheses. The scientific basis of the hypothesis also often needs explained in the introduction and background sections of papers. If you're writing a thesis or an MPH capstone type paper, you'll be able to explain this in your background. In a scientific paper, this is explained in the introduction section of the peer-reviewed journal article. The scientific basis of the hypothesis would be something that would be able to back up what the author or the investigator thinks will happen. If they're expecting an association between exposure or an intervention and a disease or the reduction of that disease, the background literature should back it up. And that background literature could be the biological basis of why an exposure would be associated with a disease. Where would the biological basis research exist? Well, it could be a toxicological study that showed that in animals, when mice were exposed to this chemical, they had this health outcome. Or it could be cell lines, or it could be molecular in nature, or it could be tissue culture in nature, or it could be animal studies from like wildlife. When these animals were exposed to this, here were the outcomes. With respect to intervention-based research that you may see in health promotion, maybe we're not looking at a biological basis. We might be looking at your hypothesis is likely true because when this intervention was employed for preventing this particular bad health behavior, it worked. So we're looking at potentially a different bad health behavior, and we have reason to believe that the intervention strategy worked for that particular bad behavior. Maybe it'll work for this bad behavior. And then that particular intervention could be backed up by the science. There might be psychological studies out there on ways of educating people or encouraging people to make better, healthy decisions. Now, actually writing the hypothesis. There are ways of writing hypotheses, and you want to include all those elements that were previously described in the research question segment. You could potentially write a hypothesis in a manner like this. Among persons in population X, we could say among persons in Appalachian counties in the United States, there will be a significant increase in, let's say, lung cancer among those exposed to e-cigarettes compared to those not exposed to e-cigarettes. You could potentially even add a year component or time component to it if you want to. There are other types of examples. It could be among persons in, we'll say, among adults in Appalachian counties in the United States, there will be a significant positive correlation between the mortality rate from COVID-19 and increasing amounts of, we'll say, poverty in that county. So there's different ways of doing this. Now, when you're looking at the introduction of scientific papers, you may find the alternate hypothesis. The alternate hypothesis may look like what we just saw there. An alternate hypothesis is what you expect to happen. Sometimes the alternate hypothesis in a paper is implied. The alternate hypothesis is different from the null hypothesis in that the alternate hypothesis provides information suggesting that there will be something happening. There will be a significant difference between this group and that group, or there will be a significant correlation. As one thing goes up, the other thing will go up or go down. There is something going on. We wouldn't do the study if we thought nothing was going to happen. We do the study, we have the hypothesis, something will be different, something will be happening. The null hypothesis assumes no association or no correlation or no difference. The null hypothesis says nothing is going on. The alternate says something is happening. The null, nothing is happening. So in the null hypothesis, the equal sign is always present. Examples of null hypotheses could be something like group A equals group B. Or if the greater than symbol is used, it's not the greater than sign that tells you this is a null hypothesis. It's that equal sign, the greater than or equal sign. Equal sign makes these examples of null hypotheses. If you're doing a study that's a correlational design, if the correlation coefficient overlaps with 0 or no correlation, if it's equal to 0, then that's going to be the null hypothesis. So let's compare the null versus the alternate hypotheses. In the null hypothesis, which are sometimes called H naught or H sub 0, we see the equal sign. Group A equals Group B. The BMI of Group A equals the BMI of Group B. There's no significant difference. But in the alternate hypothesis, the BMI is different from Group A to Group B. Now, I don't know if this would be the best hypothesis in the world because it's just saying that there would be a difference. You presumably would assume that one of them would get higher and the other would get lower. But, that's for you to figure out. In this example, we see the null hypothesis here. Group A is greater than or equal to Group B. Whatever you're measuring for Group A. It could be the COVID-19 mortality in Group A or in New York is greater than or equal to the COVID-19 mortality in Florida. And then this would be New York versus Florida again, but it's saying it's less than. Notice where the equal sign is. The equal sign stays in the null hypothesis. Again, the null hypothesis has the equal sign in this particular example of an alternate versus null hypothesis. Sometimes the alternate hypothesis, instead of being wrote as HA, it may be wrote as H sub 1. Again, the alternate hypothesis has a difference. There's a difference. There's no equal sign there. Null has the equal sign. In this last one, the null hypothesis says that the correlation coefficient equals 0. Or it could be like a less than or equal to 0. As long as there's an equal sign in there, you know it's the null hypothesis. The alternate says that there is a difference. And sometimes you'll see it as H sub A, and sometimes the A is capitalized. Usually I see it more commonly like this. In scientific report writing, in scientific papers, you may not see it this way. Often you'll only see the alternate. So it's important though to understand these basic concepts, and these concepts here will likely be a big part, or not a big part, but be a part of the midterm examination. So if you have any questions about writing a hypothesis or figuring out which one's a null versus an alternate, please let me know. And you've got my email address. And I wish you the best in preparing for your exam. And if you have questions, feel free to reach out. Thank you.